Welcome, everyone. For today's prep, we're going to start looking at the limit definition of continuity. So this is a concept that we've mentioned a few times in the context of direct evaluation. So let's start by looking at example 1, and just to see why this concept is so helpful. So let's say that this function, the given function in this example, is known to be continuous at x equals 1. And if we know our function is continuous at a particular x value, that simplifies our limit calculation process because we can use what we call direct evaluation. So normally, if we know the function is continuous at the number x is approaching, we can just do direct evaluation. And this has been one of our kind of common techniques for calculating limits. So if we do our direct evaluation in this case, we end up with natural log, and then 1 squared plus 4 over 5 square root minus 2. And if we simplify that down, we end up with the natural log of 5 over 3. Perfectly good number. Okay, so if we know a function is continuous, the limit process becomes, relatively straightforward. All right, so the question is, how do we check whether a function is continuous or not at a specific x value? So how do we know a function's continuous at x equals a? Well, the limit definition here for continuity, let's read through this. So we say a function f is continuous at this x value x equals a, provided the limit of our function as x gets close to a is equal to the function value directly at x equals a. So when we're thinking of limits and thinking of continuity, we want to think of the limit process here. This is describing the behavior of our function near x equals a. So we've seen kind of graphically, if we're doing a limit, kind of look a little bit to the left, we look a little bit to the right, we kind of see if they match up. So the limit process here is describing the behavior of our function near x equals a little bit to the left, a little bit to the right. What this function value does, f of a, what this does, this is looking at the behavior of our function not near x equals a, but what's going on directly at x equals a. So that's kind of the key concept here. The idea of continuity says a function's continuous if what happens on the left side and what happens on the right side matches up with what's happening directly at x equals a. So the left side matches up with the right side, and then another thing is what happens directly at x equals a matches up with those left and right sides. So that's kind of the idea. How we actually check that a function is continuous here, what we need to do is three things. We calculate the left-hand limit. So we do the limit as x approaches a from the left of f of x. Then we look at the right-hand limit. So the limit of f of x as x approaches a from the right. And then the third thing is we look at our function value directly at x equals a. And in order for it to be continuous, we need all three of these values to be equal to each other. So it's not enough just to check the left and the right side. So even if this limit exists, it doesn't necessarily mean that the value of this limit equals to what is going on at the function. So when we check continuity, there's three things we have to show. left-hand limit, right-hand limit, and the function value, and then all three of those values have to be equal. All right, so let's just look at some graphs. So our graphical interpretation of continuity is almost what you'd expect. Well, I shouldn't say almost. It's basically what you would expect. So a function is continuous provided its graph does not have any breaks or gaps in it. So if we have a curve, what we can do is you can imagine putting your pen down on the curve and then tracing over that curve, and you can do it in one continuous motion. You never have to take your pen off the page. So it always helps to, if we're talking about a function, if you have a picture, try drawing the picture for yourself. Try drawing the graph for yourself. And as you draw the graph, if you ever have to kind of stop, take your pen off the page, and then put it back down and keep going, well, that's an issue. But if you can just trace over the curve in one clean motion, you're good. You have a continuous graph on your hands. So in this example, this graph is continuous at x equals 2. Because what's going on there at x equals 2? The left side of the graph matches up with the right side of the graph, matches up with the point that's actually there. So all kind of three things match up. We've got our left side, we've got our right side, and then we've got our point directly at. And all kind of three are matching up. The left side of our curve is taking us to this point, the right side of our curve is taking us to that point, and then directly at that point, well, we're right where we should be. Okay. And actually, we've kind of enlarged this point at x equals 2 just to kind of consider that as the example, but technically this graph is also continuous at all other points because the same argument could be made. So if I kind of made the point at x equals 1 bigger, just to kind of emphasize that, the left side there, the right side there, and then my point directly at all match up. So not only is this graph continuous at this special point x equals 2, but it's also continuous at all these other points. Okay, so let's look at just a couple examples of graphs where kind of things go wrong. So let's start with example 2. And we're going to determine where these two graphs, whether or not these graphs are continuous at x equals 2 or not. And when we do this, we're going to really use that limit definition of continuity in our work. All right, so let's look at this first one. First, let's kind of just talk our way through this. So we have a graph of a function here, and let's just think of the kind of the intuitive drawing the graph definition of continuity. So if I were to start drawing this part is fine. All these points over here, our graph is continuous. But once I get to this right around x equals 2, I have to take my pen off the page to draw that point. And then after I draw that point, I have to take my pen off the page again, and then I have to bring it back down here to continue drawing the rest of the curve. So what happens here is I cannot draw this curve in one continuous motion without taking my pen off the page. And where the issue happens is right there at x equals 2. And you can kind of test for yourself, though. All the other points on this graph, our graph is continuous. So the only one that's giving me issue here is what's going on directly at, or what's happening around x equals 2. All right, but let's kind of prove this using our limits. So let's calculate the left-hand limit first. So let's do the limit as x approaches 2 from the left. And so if we look at our left-hand limit, Again, we imagine kind of walking along the curve here, see which point we're approaching. And in this case, it looks like we're approaching this point, and the y-coordinate for that is 1. So our left-hand limit here is 1. Okay. Then we go to the right side. So if we look at the right side, again, imagine walking along the curve, and the right-hand limit, let's figure this one out. X is going to approach 2 from the right now. And we're approaching that same point, and the y-coordinate for that point is still 1. So this is going to be 1. Okay. So now what's happening directly at x equals 2? Well, directly at x equals 2, we find the filled in point now, and the y-coordinate for that filled in point is 3. So that's us directly at x equals 2. And that means our function value here is 3. So what we found is we calculated the left-hand limit, the right-hand limit, and the function value, and all three of those values are different. So this graph is, we would say, discontinuous at x equals 2, or not continuous. And the reason is, well, these three values are not all equal. We want all three of those values to match. So because all three of these values don't match, the graph is discontinuous. Okay, let's try another one. Similar graph here. And again, let's talk our way through it. So if I imagine drawing the curve, I can trace over this part of the curve fine, no issue. I could do this part in one continuous motion. But then I have to kind of take my pen off the page to kind of jump over this hole, and then I continue on over here. So let's see what's going on in this case. So again, we go to calculate our limits. So first thing we do our left-hand limit. And our left-hand limit here is 1. So if we're looking at the left side, similar to the same graph we just did, we're approaching along this side of the curve, and the y-coordinate of the point that we're getting close to, the y-coordinate for that point is 1. So that's our limit value. Then we do our right-hand limit. So x is approaching 2 from the right. And now we're looking at this side. And again, we're approaching that same point. And the coordinate for that point is 1. So the right-hand limit is 1. And then finally, the third thing we need to do is, well, what's going on directly at x equals 2? And so we look for our filled-in point. We find x equals 2. We kind of search up or down, wherever we need to look for the filled-in point. And there is no filled-in point. So g of 2 does not exist. And again, for a function to be continuous, we need all three of these values to be exactly the same, and they're not. So we would say this one is discontinuous at x equals 2, since those three values don't match. They all have to be the same. So it's not enough that the left-hand limit and the right-hand limit match up. So yeah, the left-hand and the right-hand limit, they're all going to the same place, but what's going on directly at x equals 2, that's missing. So all three values aren't matching up. So the graph here is discontinuous. All right, so we're going to try a few more examples of these in class. What you want to do though is calculate all three of these values and see if all three match up or if they don't. All right, so we'll see you in class. Bye-bye.